Okay, so looking at inverse variation, and what inverse variation is any kind of relationship where y ends up being proportional to 1 over some value of x on the denominator. Okay, so as one increases, the other decreases, and vice versa. And so when we do it, it ends up being some kind of relationship with like k over x to the power n, which we also know is y is equal to k x to the minus n. Or if I consider that n is a real number that is negative, I could say y is equal to kxn. And so there's very much a similarity between direct variation and inverse variation. When n is negative, it's inverse. When n is positive, it is direct variation. When it is inverse variation, when I consider these types of equations, one of the things I know is that I'm not allowed to divide by 0. So x will never be 0. And it also is going to, as x gets really large, it's also, this calculation will go to 0. So there is characteristics of inverse variation, is that the x and the y-axis are asymptotes. And so that is the characteristic of inverse variation. So let's try an example here. So we know that for cones of equal volume, the height is inversely proportional to the square of the radius of the base. Oh. So for cones of equal volume, so here's a cone, and it says the height is inversely proportional to the square of the radius squared. Okay, so I know the height is inversely proportional to the radius squared. This is what this words say. And so what I can get from that is the height is equal to some constant over r squared. And so then I know the radius of 10 gives me a height of 15. So I know r is 10 and the height is 15. So I can find my k value. So 15 is equal to k over 10 squared. And so k will be 100 times 15 will be 1500. And so my actual equation is going to be h is equal to 1500 over r squared. And so there's my equation that relates h and r. So now if I look at a part, it says find the radius of the second cone of equal volumes if the height is 60. Well, if I know the height is 60, well then I can calculate my radius squared by putting the values into here, and I know the radius will be 1500 over 60, and if I take the square root of both sides, when I divide that, I end up with, this works out to be exactly 5 centimeters. I believe centimeters is my unit, and it is so. Okay, so using our equation that we find, we're able to find the radius. Now, B part says the height of the second cone is accurate to the nearest centimeter. So that means this height is not exactly 60. It means the height could be from 60.5 to 59.5. In this range is where the height could exist. So it wants me to find the range of possible radii. So if I use my equation again, I could say I'm going to go consider the upper end of height, which will be 1500 over r squared. And I know that r will be then the 1500 divided by 60.5 using this scenario down here. And so I end up, when I do this calculation, it ends up being the square root of 1500 divided by 60.5. And so if the height's 60.5, the radius is 4.98 centimeters. Similarly, if I know my height is going to be the 59.5, if I go back to here, I can call my answer back. Now let's make it 59, and we can see then that the radius is 5.98 0.02 centimeters. And so this is the range of values for radius, for the range of values for h. And finally, what is the constant of variation? Well, this value here, k, is called the constant of variation. It's also called the constant of proportionality. I've heard it called before. But it's the variable that relates the two, or the parameter, sorry, that relates the two variables together.